Jay Gunkelman, QEG diplomat, is recognized as one of the top leaders in the field of EEG and QEG. And has processed, this is no break, over 500,000 QEGs since 1970. Jay was the first EEG technologist to be certified in QEG and was granted a diplomat status in 2002. His sidekick, Dirk de Ridder. Dirk de Ridder is founder and director of Brains Research Consortium for Advanced and Innovative Interdisciplinary Neuromodulation. He's developed burst and noise simulation as novel stimulation designs for implants and is working on other stimulation devices. He's published 35 book chapters, co-edited the text of Tinnitus, and has authored and co-authored 221 papers. I don't know what he does the rest of his time, in which 199 PubMed listed. So these are the resources. I'm just going to turn these guys loose and you just hang on, okay?
Good morning, everybody. I'll start, and whenever I get lost, Jay will take over. If you have any difficult questions, Jay will answer them. But what I will do is I will give a little bit of a theoretical background and then the practical application for EEG and the practical application for neurofeedback is where Jay will then jump in. So I will do more the theoretical part and Jay the practical part. I will start with a short introduction on why do we have a brain? Because we all think it's very normal that we have a brain, but what is the main function of the brain? And there is a story in the book Eye of the Vortex, written by Rodolfo Llunas, which is a marvelous book. It already dates, I think, to 2000 or 2002, in which he describes the life story of the sea squirt, which in its larval stadium has a notochord in green and a central ganglion, which you can see as a brain and a spinal cord. Now, when it swims around in its larval stadium, at a certain moment, the sea squirt decides to go and sit on a rock, and it will never move anymore. And at that moment in time, actually, it disintegrates its spinal cord and its brain, and then it becomes just a sea squirt that sits and fixed on a rock. And based on that concept, actually, Rodolfo Llunas came up with the idea that we have a brain once we start moving around in a changing environment. And if the environment changes, there is an inherent uncertainty of what is behind the rock. Is it something edible? Will I be eaten? In order to predict what is behind the rock, actually, that's why we developed a central ganglion or a brain. And so our brain is basically, the main function is to predict the future. But you can only predict if there is recurrent statistical regularities in the environment. And so then our brain can try to predict based on just statistical information what is changing in the environment. The core function of our brain is to be a prediction machine. And this was already proposed by von Helmholtz and is later translated in what we now call the Bayesian brain, where Bayesian statistics are used for the brain to predict what is around in the environment, and then our senses have as function to basically look for evidence that the prediction is right or wrong, and then we respond when the prediction is wrong. So the only thing your brain is interested in is a wrong prediction or a prediction error. And that's, for example, why we don't feel our clothes, because our clothes is always the same stimulus. Our brain can perfectly well predict that the stimulus is going to be there, so we don't process that consciously anymore. However, we can learn to predict. We predict based on what we have in memory. And so from a practical point of view, our brains are just prediction machines that are essential once we start moving around in a changing environment, and we use information from the past, which we call memory, to predict the future. And this, of course, predicting the future is based on the current context, and it has to be related to the self, but ultimately the function of the brain is to reduce uncertainty, which is inherently present in a changing environment. And this is important for survival. As you can see here, if you encounter this, something in your brain should store it so that next time when you are in the same area, you won't try and do these things again. This is not just for natural selection, but also the same for sexual selection. So the exact same mechanism of having a brain is both good for natural and sexual selection. And if you believe in a concept of social selection, it can be beneficial for that as well. So if we simplify the brain to the extreme, and being a neurosurgeon, we can simplify things very much, then you can split up the brain in different parts. You can split it up in an anterior-posterior divide, medial and lateral, left and right, and then, if you believe in the triune brain, inside out. Jackson in the 1870s already suggested that actually the anterior part of our brain has a motor function, and the posterior part has a sensory or a perceptual function. So that is a very gross simplification, but it makes sense. And Rodolfo Llinás, the same guy from the C-squared, actually then said, well, thinking is basically just nothing else than internalized movement. So it's a motor act as well. This is not what Rodolfo Llinás himself figured out, because Aristotle in the Anima already said exactly the same thing, which is not that abnormal, because in our spinal cord, the posterior part is mostly sensory as well, and the anterior part is mostly motor as well. And since our brain is just an extension of that, it makes sense that the anterior part has a motor function and the posterior part has a sensory function. Now you can say, okay, that's a gross simplification, but even from a genetic point of view, if you look at a genetic parcellation of the cortex, actually using a clustering technique, you can find 2 clusters in the brain, and 1 to 6 are the anterior parts, and 7 to 12 are the posterior clusters. So even from a genetic point of view, our brain is divided in an anterior and a posterior part. So you've got an anterior motor part, sensory, anterior motor, sensory, posterior part. But you can also look at the brain from the midline outward, or from from lateral to medial. And there the idea is that everything which is processed on the lateral side of the brain is responding to external triggers. So if we look at that, for example, in the motor system, then you've got some areas in the brain that are related to motor function, and the premotor areas, so here in blue and in pink, are actually concerned with planning or preparation of movement, and they use information predominantly from the sensory part in order to respond to plan these motor activities. And then from the premotor cortex, the information is sent to the motor cortex to then give a motor response to the external stimuli. So the lateral part in blue is basically responding to externally cued movements, and the medial part is when you decide yourself, I will take a step forward, for example. What it means is that you have a plan of going from A to B. This planning will predominantly occur in the frontal areas, will then go to the basal ganglia, from there to the supplementary to the pink area, and then to the motor cortex. The lateral premotor areas is response to visual information that comes from the occipital cortex, auditory information, somatosensory information. It will go to the multisensory area, goes then from this green multisensory area to the blue premotor area. So from the parietal cortex to the premotor cortex, but also to the cerebellum, and from there to the motor cortex, and from there then to the red primary motor cortex. So if you look at that, then you've got two ways of activating the motor cortex. One which is internally triggered, and one is externally triggered. The externally triggered pathway uses the parietal cortex and the cerebellum, whereas the internally triggered pathway uses the prefrontal cortex and the basal ganglia. So you can say, well, so what? Why do we have that? Well, a very practical example is people who stutter. So if people stutter, normally they stutter when they want to say something, so when they use this pathway. Now, if you have somebody who stutters, just write down in your mind eye what you want to say and read it. Then they use the externally triggered, then they won't stutter. So they will perfectly fluently speak when they first imagine or have written down in their mind what they want to say, or they can sing without stuttering as well, because they will sing along, which is the external trigger pathway. So there are some practical examples that you can use in these patients. Now, so we've got the anterior, posterior, medial, lateral, and you also have an inside-out kind of division, and this goes back to the already outdated idea of Paul MacLean, which is called the triune brain. So the triune brain, and the triune brain, Paul MacLean came up with the idea that we've got a reptilian brain at the brainstem, which is basically our survival brain. It just controls our heart rate, our respiration, etc. And they're all reflexes. Then there is the primitive mammal brain, which you can find in the Ichnedia and in the platypus, which has a limbic component and is supposed to be our emotional brain. Basically, it's a dimmer of the reflexes. So the reflexes, like in our amygdala, is all or nothing, and they can be dimmed just like a light by the emotional brain. And then the modern mammalian brain, or the cortex, is basically what Paul MacLean calls the cognitive brain, and allows you to anticipate things, which will then control the dimmer to have an influence on the reflexes. So conceptually, we've got a mammalian brain, a reptilian brain surrounded by a dimmer system, and then a system that allows us to anticipate. Now, that's a very simple approach to how you can conceive of a brain as we have it now. And then of course, the brain works in an electrical way, modulated in a chemical way, and all these frequencies are actually related to one another. So whether you talk about infra-slow frequencies going to gamma or sigma, whichever you want to call, they're related in a way which we call 1 over f, or depending on how you record, 1 over f squared. So in a pink noise or a Brownian noise. And so basically what this means, that what happens in the lower frequencies has an influence on the higher frequencies as well. So how can we conceive of that in a simple way? If we've got two parts of the brain, or two modules that communicate, then what's happening in this module has an influence on this module, and the way it happens is by using lower frequencies, which you can conceive of as carrier waves. So your delta, theta, and alpha are carrier waves, and what is happening in the modules is basically very simple according to Linus's idea. Beta, especially beta 1, is a kind of a prediction frequency, and then gamma is a prediction error frequency. So basically, you make predictions in beta, and gamma says it's wrong or it's right. It's a prediction error. So basically, a prediction error means there is a change. So if you see gamma, it just means there is a change, but the change has to come up and go down very, very rapidly. If it's there constantly, you are in trouble. So to conceive of that is that the information or the communication between those two modules is transmitted in a carrier wave. Here, for example, a theta wave, and on top of that, you've got nested a higher frequency, a gamma or a beta, if it's a prediction error, or if it is a prediction. So if you look at the raw EEG from this point of view, you can use a Fourier transform to come up with the different frequency bands, and those frequency bands can be purely theoretically be split up in carrier waves and information waves. And where does this idea come from? Well, because there is different generators and there is different distances that are carried by these waves. So delta waves are generated from an evolutionary point of view. Buzaki has suggested that the lower frequencies are evolutionary extremely old. So for example, the reptiles predominantly use delta activity, not that they don't have any higher activity, but the phylogenetically older species are using delta waves, and then the more recent evolutionary species actually accelerate or develop faster waves as well. So if you look at then, bring it back to Paul MacLean's idea that our reptilian brain, the brainstem, then it's not as a surprise that it functions in low frequencies. Also the reticular nucleus of the thalamus, which is a shell that lies on the thalamus that blocks information transmission, and the cortex create delta. Theta activity is predominantly generated in the septal nuclei and the hippocampus, and alpha is predominantly generated in the thalamus and the cortex.
The format is interactive, which means interruptive. It's, I think, crucial for you to understand delta, theta, alpha, beta generators. And delta is generated by sheet dipoles. A dipole is a plus and a minus, but this happens in a large sheet. Whenever there's a lack of an input to the cortex, the cortex has an emergent delta rhythm. If you have an absence of an input to the cortex, like you have during sleep, like you have during very early life where your white matter hasn't wired up your cortex, these slow rhythms are predominant. However, the delta is not the only rhythm, obviously. Theta rhythms are the next frequency up. And the theta rhythm basically is generated limbically. The septal nuclei provide acetylcholine to the temporal lobe limbic structures, which generate the rhythm within the limbic system. However, the International Federation position paper on EEG rhythm generators tells you that when you see a theta frequency, you have to differentiate whether it's limbically generated theta or slowed thalamocortical alpha. They can be in the same frequency band, but they mean totally different things. And if you see slowed alpha, you need to speed up the alpha to fix it, and that requires norepinephrine to speed up the alpha. If you have theta excess, for instance, in ADD, this is a methylphenidate responder because of a dopamine deficit. The difference between them predicts totally different medication interventions, and obviously means different things are wrong. Alpha rhythms are thalamocortical thalamic. It's a feedback loop. It requires both the thalamus to fix the frequency, to pick the rhythm frequency, the cortex to generate the voltage, and if that loop doesn't exist, you don't basically end up with the alpha rhythm. It's not that easy. If you see a theta frequency, you need to actually look to see, if you see theta, typically you see it frontocentrally. If you see a theta frequency up there, you look to the alpha at the back of the head to see if that's slow or not. You can test alpha by opening and closing the eyes. In neurology, they don't say alpha is 8 to 12. That may be the right answer on some exams, but the thalamus can go as slow as about 3 hertz and up to about 16 or so and still be rhythmic. It makes activity up to 20 or so, but it's only rhythmic up to about 16. At that point, you can't line up the frequency peaks, so it desynchronizes. So alpha is actually from 3 to 16 as a rhythm, but that's not the right answer on anyone's exam. So don't quote me when you take an exam and then try to argue the answer. You'll fail that exam because that's only the real neuroscience. It's not the right answer. So alpha could be slowed down to the theta frequency, and it can actually speed up into what you normally would consider SMR as an example, which is a thalamocortical rhythm, and it's a little above that 12 hertz range. The beta 1, beta 2, and gamma are generated in small local neural pools. Beta is a cortical rhythm, but where's gamma generated? Well, gamma is not generated anywhere. It's generated everywhere that you have a neural network that's bound. Gamma emerges from bound networks. It's a resonant property of having a network that's bound. And as such, if you create a network, it has a resonant frequency. Like if you make a bell, it has a frequency it will ring at. So your brain creates a network, and that network temporarily generates gamma. We'll look at that obviously as an important issue later, but I think it was important for you to end up identifying each of these rhythms as having separate generators. And obviously, alpha is generated in the thalamus, but the thalamus isn't one thing. First of all, you have one in each hemisphere. You have a left and a right thalamus, but it also has a lot of subnuclear bodies that project to different locations. So if you actually get down into it and you study the thalamus a little bit more in detail, there's lots of nuclear bodies within the thalamus. It's not just a single entity. And there was obviously a question. Be loud.
What are the frequency ranges that you would say beta 1, beta 2 and gamma would be? What are the frequency ranges? Frequencies of beta 1, beta 2, gamma?
Beta 1 basically is just above alpha, but these are artificial separations. They actually are slightly different, different individuals, very much like your alpha can be fast or slow. Your theta can speed up some. You can actually have theta rhythms that start to pump themselves up into the alpha band a little bit, so you have to be very cautious in interpreting what things are. Look where they're located and how they respond to different circumstances, and that's the only way you can end up differentiating them. If you go back in time, there was delta, theta, alpha, and beta, and there wasn't beta 1, beta 2. Gamma didn't exist for most people in the field back a long ways ago. Neurofeedback as a world unto itself has people that sell devices that can train gamma, and they basically will tell you that gamma is good because they want you to buy their device and train gamma with it. But gamma is not always good.